welcome to today's afternoon session. Before the session begins, let me announce one thing for the invited speakers. Please send your file after your talk to our secretary, Ms. Guo, and then she will upload your file to the website. All right, so in today's afternoon session, there will be three speakers. The first talk is given by Professor Cenke Xu. He's gonna continue his lecture series number 2 on field theory description and classification of almost topological states. Let's welcome him.
Okay, yeah, so I'm going to continue what I started this morning. So this morning we discussed the field theory description and also how to use field theory to read off the boundary states of all the SPD states, and how to use field theory to expose, how to construct those SPD states. And as I said this morning, using the field theory is very easy to see that all those higher dimensional SPD states, they're basically constructed by decorating some defects, either domain wall or vortex, or sometimes even monopole with some lower dimension SPD state. Then we proliferate or condense those defects, then we get a higher dimension SPD states. Okay, so now I'm going to show you how to use the field theory to derive or calculate the ground state wave function of those SPD states. So the example I'm going to show you is the 3-dimensional SPD state with, U1 times U1, and this is a semi-direct product time inversal symmetry. And eventually I'm going to break U1 cross U1 to just one U1. But let me start with U1 cross U1 times time inversal symmetry. And this is a semi-direct product. So what it means is that the U1 operation and also the time inversal, they do not commute. Okay. So what it means is that, for example, if I consider boson operator B, under U1, it becomes it's rotated by a phase angle. But if under time inversal transformation, it goes to B itself, then these two operations, they do not commute with each other. In this case, we call U1 and time inversal, they are semi-direct product. Yeah, a semi-direct product.
Oh, okay.
Yeah, yes, the semi-direct. Yeah. The reason they do not commute is that here I do U1 first, but if I do time inversal, because time inversal also contains complex conjugation, so it's going to change e to I theta to e to minus I theta. Okay. But if I do time inversal first and do U1 later, it's going to be just e to I theta. So they do not end up with the same result. So in this case, we say U1 and time inversal, they do not commute. So we say this symmetry is going to be a semi-direct product. Okay? So you can see that in physical world, the time inversal and the U1 charge symmetry of electron is going to be a semi-direct product. Because time inversal, all time inversal due to electron is that there's an I sigma y there, but it basically just still take C to I sigma y c. You can show that they still do not commute with each other. So in physical world, the electron, time inversal and U1 charge symmetry, they do not commute. It's a semi-direct product. Now how do we? This is a U1 semi-direct d to t. Okay. Now how do I define a symmetry the U1 direct product d to t? If I want to define this kind of transformation, the U1 still go to a phase angle times B, but time inversal will go to either plus minus B dagger. So these two operations will commute with each other. The reason is that now if I do time inversal on the top line, is going to e to minus I theta B plus minus. Okay. And the bottom line is the same if I do U1. diagram. Okay, so now you can see that if I want to define a U1 and time inverse that commute with each other, then the time inverse will have to be combined with a particle Hall transformation or charge conjugation. Okay, and also you can see that suppose I define a boson, for example, as some spin operator. Okay, then this boson, time inversal, and this U1 symmetry will commute with each other. Is that clear? Yeah. Okay. So in the for example, bismuth selenium, bismuth telluride kind of ordinary topological insulator, if you want to write down its symmetry, it should be U1 semi-direct times time inversal. It's not a U1 direct product time inversal. Okay. The physical topological insulator should be U1 semi-direct time inversal. So this kind of symmetry, because we consider boson system with this symmetry, which we can also call this kind of boson system is the boson topological insulator, because it has the same symmetry as the fermion topological insulator, the U1 semi-direct times semi-direct product time inversal symmetry. Okay, so this is the action or field theory describing this kind of boson SPT state. And actually, the 5-component vector n will be the one component, and the second 2 component will be the real and imaginary part of the first boson, which rotate under the first U1, and the 4th and the 5th component will be the real and imaginary part of the second boson, which rotate under the second U1 symmetry. Okay, and as I said this morning, if you want to calculate the wave function, what we do is that we calculate this kind of matrix element between the ground state and the 2 different field configurations, and I do the path integral and just fix the time equals plus infinity equals to one configuration, and time equals minus infinity equals another configuration. Okay, this is how we do that calculation. Okay. And after we do this path integral, we can show that the ground state wave function will look like this. So ground state wave function in the strong coupling limit, if I take the coupling constant g to infinity, the ground state wave function can be calculated in the method just mentioned precisely. So the wave function will look like this. It's a superposition of all the configuration of the O5 vector, all the configuration of the 5 vector, and there's a Witten phase factor. Okay, there. And this phase factor, the physical meaning is also very simple, because now I'm talking about a 3-dimensional space, okay? And because the wave function has no time coordinate, this means that the vector n is a mapping from the 3-dimensional physical space to the 4-dimensional target space. The target space is a 4-dimensional sphere. So n is a mapping from a 3-dimensional sphere to a 4-dimensional sphere, and this phase factor precisely correspond to the area or the volume enclosed by the image of the mapping. Okay, this area. Okay, this area. Okay, so this is the wave function. But now you can see that this wave function seems to have a lot of symmetry, right? Because this vector n has some O5 symmetry, which is so much bigger than the actual symmetry I assumed. So I need to break the O5 symmetry down to the physical symmetry. I need to break the O5 symmetry down to the U1 time inverse symmetry as I mentioned. So how do we do that? First of all, we can try to integrate out the phi 0. It's phi 0, the first component. So now the phi 0, okay, the expansion value of phi 0 must be 0, because the system preserves time inversal symmetry. So any component of the 5-component vector must be 0, but have zero average value in the system. Okay? Because phi 0 is 0, it means that the rest 4 components, n2, n3, n4, and 5, will prefer to rotate on the equator of the target space. Or they rotate on the equator of target space. Okay, then this means that this term will reduce to the following term. Okay, we'll do the following phase factor. Okay. The following phase factor will look like this. It's a superposition of all the configuration of the 4-component vector. Now the 4 component become just n2, n3, n4, and 5. The 4-component vector, but with a -1 to the Skyrmian number of the 4-component vector. We know that in a 3-dimensional space, a 4-component vector can have a Skyrmian-like configuration. And this Skyrmian is correspond to pi 3 S3 equals to z. Is that clear? Right. So now I have a reduced one component because I assume that the fifth component has average value 0, so it always prefer to rotate on the equator, and this equator becomes a three-dimensional sphere. So now the wave function becomes a mapping from a three-dimensional space to an internal three-dimensional sphere space. Okay, so it's classified by the Skyrmian. Sorry?
You fix some axis in S4 and then you
yeah,
some S3. That's why you
because of phi 0 has 0 average value. Right? So it means that phi 0 is always 0, so it means that it always rotate on the equator, right? So if the system has the O5 symmetry, then the vector can be anywhere, right? Can be anywhere. But because system doesn't have O5 symmetry, right? So and phi 0 has 0 average value, so it means that it always rotate on the equator, then this term becomes a Skyrmian number term. Okay? So now the wave function becomes the superposition of all the configuration of the O4 vector with a -1 to the total Skyrmian number in a three-dimensional space. Okay, so step 1. Then we need to further reduce the symmetry. Okay, so symmetry is still too high. Symmetry is still too high. Symmetry is still O4. We need to reduce O4 to U1 cross U1. So this is very easy. So we can ask this question. So under the O4 to U1 cross U1 symmetry breaking, what does a O4 Skyrmian look like? Okay, what does the O4 Skyrmian become after I break the O4 symmetry down to U1 cross U1? Okay, we know that for a system with U1 symmetry, the most obvious topological defect is a vortex line in 3 dimensions. Okay, vortex line in 3 dimensions. So it turns out that the O4 Skyrmian, if I break the O4 symmetry down to U1 cross U1, then the O4 Skyrmian will become a linking between two vortex lines. Okay, this is something you can check. Okay, you can take an O4 vector and make it form a linking between two vortex, and then calculate Skyrmian number. It will be 1, precisely 1. Yeah, exactly. I'm saying that under, if you start with the O4 Skyrmian and break the symmetry down to O2 cross O2, that Sarton will become a linking. Yeah, pi 1 on the O2. Yeah, it will reduce to that topological defect.
So is the total vortex number 0?
What do you mean by total vortex number?
Well, I mean the entire configuration there.
Well, it should be 0 because because the vortex loop is going to be the plus vortex and the minus vortex, right? So it's 0, right? And also the O4 Skyrmian, as I said before, so O4 Skyrmian is a local object. A Skyrmian is always a local object, but a vortex is not a local object. Right? For example, if I stand as an infinitely far away from the vortex, I can still see the vortex as long as I go a very large loop. I can still see the vortex. But if there's a Skyrmian in the center, there's no way I can see the Skyrmian, even if I go a large loop, because Skyrmian is a local object, but the vortex is not. But the linking of two vortex loop again is a local object. Becomes a local object. Okay. So now the wave function under the symmetry breaking to U1 cross U1 becomes a superposition of all the boson configuration, but with a -1 to the total linking number of the vortices. Okay, become this vortex, but become this wave function. Okay, this is the wave function for this U1 cross U1 for time inverse symmetry SPT phase. Okay, so what does this wave function mean? We know that in the physical system, a vortex loop cannot end. Right, cannot end in the bulk. Okay, like superconductor vortex loop cannot end if it's a superconductor phase. But the vortex loop can end as the boundary. Okay, vortex loop can end as the boundary. So let's consider the two vortices as the boundary. So this is the red vortex and green vortex. So both of them has a vortex line attached to it. So now let's take the green vortex as a boundary, encircle the red one by 2 pi. Okay? Encircle the red one 2 pi. Then there will be some braiding between the vortex line and the bulk. So we can continuously deform the braiding and make like this. So it means that after the braiding process, the final configuration compared with the original configuration, the only difference is that it increased by 1 linking number in the bulk. This means that this process will give you a phase factor -1. Is that clear? This means that these two vortices as the boundary will become a mutual semian. Okay, they become semian. This vortex, this vortex, they have mutual semian statistics. Okay. Okay. So now suppose I break 2U1 under 1U1. If I break 2U1 under 1U1, what happens is that this symmetry breaking will bond these two vortex lines together. Right? I no longer have two vortices, I only have one vortex line. Okay? And when the vortex line ends as the boundary vortex will be a fermion, because we know that a bound state between two semians will be a fermion. Okay? So this is a prediction. It means that the vortex as the boundary of a 3D bosonic SPD will be a fermion. That's the distinction between ordinary SPD. Okay. So after I break the 2U1 down to 1U1, you can see that the two vortices will be bound together, but it still memorizes this linking information. This means that under the symmetry breaking, the U1 vortex will be a ribbon. Okay, it itself is a ribbon. It remembers the ribbon information. And the ribbon can twist, as a twist. So the ground state wave function for this U1 semi-direct times the time inversal symmetry, the ground state wave function will be a superposition of all the U1 configuration with a -1 to the twisting number of the ribbon. Did I go too fast? Yeah, but you will receive my slides later, so you can check that. Okay. Well, anyway, so this is the wave function that we can derive from the field theory. Okay, so everything boils down to a U1. I mean, the fact that we introduce the O5 vector eventually becomes that the U1 vortex becomes a ribbon, and the -1 attached with every ribbon configuration in 3-dimensional space. Okay, this is an illustration. This is an illustration for why the vortex as a boundary will be a fermion. Okay, if I break 2U1 down to 1U1, then every vortex as a boundary will be attached with two different flux lines, the red and green. So now if I exchange them, there will be some braiding or linking between the vortex line, and again, this kind of linking can be deformed into this configuration. Okay, then this configuration compared to this one, so after exchange, compared to before exchange, just increase one linking number. So again, you will get a minus sign, so it's a fermion. Okay, so vortex and boundary will be a fermion. So this is the physical consequence of the boson SPD. Okay, the physical consequence of the boson SPD is this. There's a fermion emerge from the system as the boundary. Okay, so a fermion will emerge as the boundary. Okay, so well, actually we can also do this for all the other SPTs. So you can see that, the difference between the SPD wave function and in ordinary boson insulator wave function, just in the sign structure. Okay, for ordinary boson wave function, the sum over some configuration without any sign. But for SPD wave function, the wave function will sum over some configuration with some sign attached to it. And that sign is the key information we distinguish SPD from ordinary quantum disorder system bosons. Okay, that's the only, in the wave function, that's the only difference. Okay, so now we move on to the next part. So, SPT is a system with some global symmetry. But for a system with global symmetry, we can always couple the global symmetry to a gauge degree freedom and make it a gauge theory. Okay, make it a gauge theory. And for a discrete gauge theory, the discrete theory will always introduce some topological defect. Like we know that for the Topological model, for Topological model, we have an E and M excitation, and they have a mutual semian statistics. So a discrete gauge theory will always have some anions, and anions will have some strange statistics. Okay, so we can ask this question: if I take a boson SPT and I couple it to gauge field, so what kind of topological order do I get? So what kind of anion statistic do I get? Okay, so I'm saying that this kind of information can also be read off from the field theory. So for example, let me consider a two-dimensional SPD phase with a Z2 symmetry. Again, this is an old theory, the old equation. It's an O4 non-sig model, and the Z2 symmetry will change the sign of all the four components of the O4 vector. Okay, So our goal is to couple this system to a Z2 gauge field and calculate the statistics when we braid those anions of the system. Okay, so first thing we do is that we enlarge the Z2 symmetry to a Z2 cross Z2 symmetry. But eventually we are going to break down to Z2 again. But first let me enlarge the 1Z2 to 2Z2 symmetry. So the first Z2 symmetry will change sign of the N1, N2, but does not change sign of N3 and 4. The second one will change sign of N3 and 4, but does not change sign of N1 and 2. Okay. And we know that once we couple a system to a Z2 gauge field, the gauge field will introduce some Ison excitation. And the Ison corresponds to a pi flux. Okay. Basically, it's the M excitation in the Topological model, that we have seen before yesterday. Okay. So the M excitation in the Topological model is a Ison in the pi flux, and we know that a pi flux is always bound with a half vortex. Is that clear? Right. A 2 pi vortex is always, a 2 pi flux is bound with a single vortex, then a pi flux is bound with a half vortex. This means that the Ison of the first Z2 gauge field will be bound with the half vortex of N1 and N2, and the Ison of the second Z2 gauge field will be bound with the half vortex of N3 and 4. Okay. Then let's consider the braiding between these two Isons. So let's create a pair of the first Z2 Ison and create a pair of the second Z2 Ison. And let them braid in the time and then annihilate them. Let's consider this process. Okay, consider this process. Okay. As I said before, an O4 skirmion or an O4 instanton, when it breaks the O4 symmetry, it corresponds to the linking between two vortex lines. Okay. So now this is the linking between two half vortex lines. So this corresponds to 1/4 O4 instanton. Correspond to 1/4 instanton. Question?
Just a terminology. What is Ison? What is it?
Oh, sorry. Yeah. Okay. Let me explain what Ison is. Yeah, let's consider a lattice boson theory. Okay, so let me define a boson operate on every lattice site, and I define a Z2 gauge field on every link of the system. Okay, so this system have a Z2 gauge transform, has a Z2 gauge symmetry, which is that B J go to beta J Bj, and the sigma Z Ij go to. Okay, this is a Z2 gauge transformation, and it's a local transformation because either takes a value plus or minus 1 and it can be arbitrary on the entire lattice. So once I couple this to a boson system, then we can consider the configuration of sigma Z like this. Okay. Let's imagine sigma Z is always plus 1 on the entire lattice except for these links. Let's imagine sigma Z is minus 1 on these links, but plus 1 on the other links. Okay. Then now let's give the system this kind of a sigma Z background and try to minimize the system, and minimize the energy of the system. Try to minimize this. So let's first rewrite this term as this. Okay, rewrite like this. So the phi is the angle of B. Is that clear? Okay, it's like Josephson junction. Okay, Josephson junction. Okay. So if sigma Z is 1 on all the link, it means that the system will favor phi equals to phi here equals to phi here. Okay. But because sigma Z is a minus 1 here, minus 1 here, minus 1, it means that phi here will want to be different by pi from this phi. Then it means that the minimum energy configuration attached to this background will be phi is 0 here and is pi here and rotate continuously like that. Okay, there's a branch cut. Okay, so this is the half vortex. Okay, and we call this is a visor. Okay. This is what I mean by couple system to a Z2 gauge field. Okay. And this visor is the M excitation introduced in a toric code model. Okay. So that means that if I couple this system to a Z2 cross Z2 gauge field, then the two visors, each of them will be bound with a half vortex. And when I braid them in space-time, this kind of process will correspond to a 1/4 instanton, 1/4 O4 instanton. Right? Before I said that the instanton, O4 skirmion or O4 instanton correspond to a linking between two full vortices. But now I have two half vortices linking in space-time, so they correspond to a 1/4 instanton. Okay. Okay. So now. Okay, so what's the meaning of this theta term? I take theta to 2 pi here. Okay, 2 pi. 2 pi means that if in the space-time I have a 1 full instanton, it will contribute phase 2 pi. But if I have a 1/4 instanton, it will contribute phase pi over 2. Is that right? Okay. This means that if I take one visor and encircle the other one, the system will gain Berry phase pi over 2. Right, we get Berry phase 1 pi over 2. Okay. It means that these two, yeah. Okay. Okay, so now if I break the 2Z2 symmetry down to 1Z2 symmetry, let it be break 2Z2 to 1Z2, then this means that these two visors will have to be bound together. Okay, again, be bound together. Okay. So now using our previous figure, we can show that now if I take these two bound state and do this braiding, it will gain phase factor -1. It will get phase factor -1. It means that this visor will be a semion. Okay, will be a semion. So this is precisely the physical consequence of the Z2 SPD phase. So once I couple the system to a Z2 gauge field, the visor on the system will be a semion. We have semion statistics. Okay, and also anti-semion statistics if I consider anti-vortex into vortex. So this is the physical consequence of gauging the Z2 SPD. So if I take an ordinary, Z2 system, ordinary system with Z2 symmetry, and I couple it to a Z2 gauge field, then I would get a toric code model. Okay, that's an ordinary system. But because I'm considering Z2 SPD, after I couple to Z2 gauge field, I would get a double semion theory. I would get semion statistics between the visors. And this comes from just by counting the number of instantons in the space-time. Okay, we call it field theory. Okay. Yeah, okay. Okay. So now let's move on to 3 dimension. Okay, let's move on to 3 dimension. So in 3 dimension, what kind of statistics can we have in 3 dimension? So first of all, in 3 dimension, we know we have boson and fermion statistics. Okay, that's the ordinary one. So what about topological excitations? In 3 dimensions, some topological order has a loop excitation, okay, and also point and particle excitation. And it's well known that there can be some non-trivial statistics between loop and point and particle. Okay? For example, let's consider a 3-dimensional superconductor, ordinary 3-dimensional superconductor, coupled to a dynamical U1 gauge field. Okay? Then inside the superconductor, we have a vortex loop, okay, vortex line. And also we have electron. Because the vortex line carries a pi flux, it means that if I take an electron and move it through the vortex line and take out, go back to itself, it will gain -1. Okay, this is an illustration for the statistics between a loop and a particle in 3-dimensional space. Okay, this is the most well-known statistics in 3 dimensions beyond boson and fermion. Okay, we can have this between loop and a particle. But actually,